this lesson, we're going to start by talking about neural networks and why they are so incredibly exciting. Truth be told, I've been looking forward to talking about neural networks for the most of this course. One of the reasons is that you and I have some things in common with this machine learning framework. You see, artificial neural networks were inspired by our desire to understand the human brain. The thinking was that maybe, just maybe, we could able to understand ourselves better if we were able to build a model of how the human brain worked. And at the same time, we're asking ourselves a very different question. If computers were getting more and more powerful, then why are they so bad at certain simple tasks, like telling the difference between a dog and a cat? Looking at things like Moore's law, you would think that we would be there by now, right? More transistors, higher clock speed, more processing power, and faster calculations. Faster than the human brain in many respects. And yet, raw computations only took us so far. There is only so much that can accomplish with the logic of if and else statements. As amazing as the if else statements are, it's still the programmer who has to sit down and explicitly write all that code. The computer itself couldn't learn anything. But this very point brings us back to another question. How does learning happen anyway? How does our human brain actually work? Well, if we take the brain and put it under a microscope and then we examine the cells that make up our brain, then we see that the human brain is comprised of approximately 10 billion neurons. And all of these neurons are connected to each other. Each neuron is actually connected to about 10,000 other neurons. How are these neurons connected? Well, here is the schematic. This picture here represents an individual neuron. And on the left side and the right side, you see these like funky purple lines coming out. And there is two types of lines that come in and out of a neuron. You see, neurons actually receive signals from other neurons via their dendrites. So, on one side of the neuron, you've got these inputs. And once a neuron receives a signal, it might pass the signal on, right? And the neurons pass these signals on the other side of the cell, namely through their axons. This is where they transmit their output, the signals themselves being transmitted between these dendrites, and these axons are electrical and chemical. If a neuron receives many signals from the previous neurons, then it will activate and transmit the signal. In other words, if the sum of the signals from all of the upstream neurons is strong enough, then this neuron will pass the signal on through its axons to the other neurons downstream. And then this process repeats itself thousands and thousands of times over. The key though is that a neuron only fires if the total signal received at the cell body exceeds a certain level or a certain threshold. The crazy thing though is that our entire brain is composed of these interconnected transmitters. Individually, they are all very simple processing units. Suppose all of these dots here represent an individual neuron. I've got 3 on the left, 1 in the middle, and 4 on the right. And all of these neurons are connected. And I'm going to draw these arrows between them. Now, not all connections are created equal. I've drawn some of these arrows thicker than the other ones. But let's focus on the blue neuron in the middle. When the pink neurons upstream fires, they will pass a signal along to our blue neuron. And this neuron will take the weighted sum of all of its inputs. So, the blue neuron will consider the signals that it's getting from the neurons that fired. as well as the signals from the neurons that didn't fire. And this means that the blue neuron itself might or might not fire. Whether or not it fires is determined by the total input that it has received. This total input has to exceed a certain level or a certain threshold. Now, our blue neuron did indeed receive a very strong signal by two of its strongest connections. So indeed, it does fire. So it gets triggered and it will pass the signal on to all of its 10,000 neurons that are connected to it. So this was the line of thinking that led Warren M.C. McCall and Walter Pitt to create a computational model for neural networks all the way back in 1943. Individually, each neuron is not complicated. It either fires or it doesn't fire based on a threshold. But working together, the brain can nonetheless perform very complex tasks. But the one thing we didn't talk about yet is how learning happens. In 1949, a Canadian psychologist named Donald Hebb published this theory. He pointed out that the neural pathways are strengthened every time that they are used. If two neurons fires at the same time, the connection between them is enhanced. The concept is essential to how humans learn. According to Donald Hebb, it's the connection between the neurons that matter. So, for the sake of argument, let's say you are trying to learn a foreign language. Let's say Japanese. Every time you say something in Japanese, certain neurons in your brain start firing. Every time you practice speaking, the connections between these neurons get stronger. And that's why the more you speak, the easier it gets to express yourself and remember the words. Activating the neurons again and again strengthens the connections between them. And there is actually a word for the strength of a connection. This strength is referred to as weight. So, as you are practicing speaking in your foreign language, you are effectively training your neurons and changing the weight between them. So, this concept was Donald Hebb's big insight. The learning comes down to adjusting the weight between the neurons. And this is also the model that artificial neural networks are based on. So, given that scientists started working on this all the way back in the 1940s, the question then becomes, did we succeed in modeling the human brain based on neural networks? Since we've been at it for a long time after all, right? Well, not quite. Even though the biology provided the inspiration for artificial neural nets, we still got a long way to go figuring how the brain actually works. So far, we haven't come close to modeling the sheer complexity of the human brain. But neural networks have proven themselves to be extremely good at tasks which are very different for traditional computers. Say, like image recognition. So now, where does all of this leave us? Well, we've covered a couple of very important points already. Neural networks are composed of individual nodes or neurons. All of these nodes are connected to each other, and the strength of these connections are called the weights. And the process of learning, both for humans and for machines, involves adjusting the weight between the nodes. We will be talking a whole lot more about this in the next lecture. I'll see you there. Take care.